Welcome to a journey through the biggest secrets of the Milky Way. Over the next 2 hours, we will explore the hidden mysteries of our home galaxy, the invisible forces that shape it, and the enigmas that continue to puzzle astronomers across the world. Whether you're here to fall asleep, to study, or simply to relax while learning about the cosmos, take a deep breath, settle in, and let the wonders of the Milky Way unfold before you. The Milky Way is not just a collection of stars scattered randomly across the darkness. It is a living structure, a dynamic system governed by forces we're only beginning to understand. Beneath the beauty of its spiral arms lie secrets that challenge everything we thought we knew about galaxies, space, and time itself. Some of these secrets are hidden in plain sight. Others are concealed behind veils of dust cloaked in darkness, or buried deep within the mathematics of physics. But each one reveals something profound about the universe and our place within it. Let's begin our gentle journey through the biggest secrets of the Milky Way. The Milky Way appears to us as a soft band of light stretching across the night sky. But this view is deceptive. What we see is only a fraction of what exists. The true structure of the Milky Way is far more complex than the naked eye can perceive. The galaxy is not a simple spiral. It is a barred spiral galaxy, meaning it has a massive bar-shaped structure of stars cutting through its centre. This bar extends for approximately 27,000 light-years from end to end. It rotates slowly, like the hand of a cosmic clock, shaping the orbits of billions of stars around it. But even this bar is not the full story. Recent discoveries have revealed that the Milky Way contains additional structures that were entirely unknown until the last few decades. These structures are invisible to traditional telescopes. They do not emit light. They do not reflect light. Yet they are there, massive and influential, sculpting the galaxy from within. One of these structures is called the Fermi bubbles. These are two enormous lobes of energy extending above and below the galactic plane. Each bubble stretches for 25,000 light-years. Together they span 50,000 light-years, half the width of the entire galaxy. They glow faintly in gamma rays, the highest energy form of light, invisible to the human eye. No one knows for certain what created the Fermi bubbles. The most likely explanation is that they were formed by a massive outburst from the supermassive black hole at the centre of the Milky Way millions of years ago. This black hole, usually quiet, may have consumed an enormous amount of matter in a short time, releasing a burst of energy so powerful it tore through the galaxy like a shockwave. But the Fermi bubbles are not the only invisible structures. There are also vast streams of stars orbiting the Milky Way. These streams are the remnants of smaller galaxies that were captured and torn apart by the Milky Way's gravity. As these smaller galaxies fell inward, they were stretched and pulled, their stars scattered into long ribbons that now orbit our galaxy like cosmic rivers. One of the most famous of these streams is called the Sagittarius stream. It was formed from the Sagittarius dwarf elliptical galaxy, a small galaxy that is currently being devoured by the Milky Way. Over billions of years, the gravity of the Milky Way has pulled stars out of the Sagittarius galaxy, creating a stream of stars that wraps around our galaxy multiple times, like a thread wound around a ball. There are dozens of these streams now known to astronomers. Each one tells the story of a galaxy that came too close to the Milky Way and was destroyed. Each one is evidence that our galaxy is not passive. It is a predator, consuming smaller galaxies to fuel its growth. Beneath all of this, invisible and undetectable except through its gravitational effects, lies the dark matter halo. This halo is a vast sphere of dark matter surrounding the Milky Way. It extends far beyond the visible edges of the galaxy, reaching out into intergalactic space. It contains more mass than all the stars in the galaxy combined. Dark matter does not emit light. It does not interact with ordinary matter except through gravity. We cannot see it. We cannot touch it. But we know it is there because of the way it bends space and affects the motion of stars. Without dark matter, the Milky Way would fly apart. The stars in the outer regions of the galaxy are moving so fast that they should escape the galaxy's gravity. But they do not. They are held in place by the gravitational pull of the dark matter halo. The nature of dark matter is one of the greatest mysteries in physics. We do not know what it is made of. We do not know how it formed. We do not even know if it is made of particles at all. Some scientists believe it could be a modification of the laws of gravity itself. Others think it could be a type of particle that has not yet been discovered. But whatever it is, dark matter is the hidden skeleton of the Milky Way. It is the invisible framework that holds the galaxy together, the structure upon which everything else is built. And so, even as we gaze up at the Milky Way and see a river of stars, we must remember that what we see is only the surface. Beneath the light, hidden in the darkness, lie structures and forces that we are only beginning to understand. At the very heart of the Milky Way lies one of the most mysterious and powerful objects in the universe. It is called Sagittarius A star, a supermassive black hole with a mass 4 million times that of our Sun. It sits at the exact centre of the galaxy, anchoring everything around it. For most of human history, we did not know this black hole existed. The centre of the Milky Way is hidden from view by thick clouds of dust and gas. These clouds block visible light, making it impossible to see what lies beyond them. It was only with the development of infrared and radio telescopes, which can penetrate the dust, that astronomers were able to peer into the galactic centre and discover what was there. What they found was astonishing. At the very centre of the galaxy, there is a region of space where stars move faster than anywhere else. These stars orbit an invisible point, circling it at speeds of thousands of kilometres per second. By measuring the orbits of these stars, astronomers were able to calculate the mass of the object they were orbiting. The result was undeniable. There was a black hole at the centre, massive beyond imagination, pulling everything around it into a tight, fast orbit. This black hole is not visible. Black holes do not emit light. They are regions of space where gravity is so strong that nothing, not even light, can escape. But we can see the effects of the black hole on the matter around it. Gas and dust near the black hole are heated to millions of degrees as they spiral inward, emitting X-rays and radio waves. These emissions reveal the presence of the black hole, even though the black hole itself remains invisible. Sagittarius A star is relatively quiet compared to other supermassive black holes. In many galaxies, the central black hole is actively feeding, consuming vast amounts of matter and releasing enormous amounts of energy. These active black holes can be so bright that they outshine the entire galaxy around them. But Sagittarius A star is dormant. It is not feeding on large amounts of matter. It is calm, waiting. But this calm is deceptive. There is evidence that Sagittarius A star was not always so quiet. The Fermi bubbles, those enormous lobes of energy extending above and below the galaxy, are likely the result of a past outburst from the black hole. Millions of years ago, the black hole may have consumed a massive cloud of gas or even a star, releasing a burst of energy so powerful it blew material out of the galaxy at nearly the speed of light. If such an outburst were to happen again, it would have profound effects on the galaxy. The burst of energy would tear through the galactic disk, heating gas clouds, triggering star formation in some regions, and disrupting it in others. Life on planets near the galactic centre could be sterilized by the intense radiation. Even here, 26,000 light-years away, we would see the effects as a brightening of the galactic centre in the sky. But for now, Sagittarius A star is quiet. It sits at the centre of the galaxy, a silent giant, waiting. Around the black hole, in a region spanning just a few light-years, there is a dense cluster of stars. These stars are some of the oldest in the galaxy, formed billions of years ago in the chaotic conditions of the early universe. They orbit the black hole in tight, fast orbits, some completing a full orbit in just a few decades. Observing these stars has allowed astronomers to test Einstein's theory of general relativity in one of the most extreme environments in the universe. According to general relativity, space and time are not fixed. They are warped by the presence of mass and energy. Near a massive object like a black hole, space and time are warped so severely that they behave in strange and unexpected ways. One prediction of general relativity is that the orbit of a star around a black hole should not be a perfect ellipse. Instead, the orbit should precess, meaning the ellipse itself should rotate slowly over time. This effect is tiny for most objects, but near a supermassive black hole, it becomes measurable. In 2018, astronomers observed one of the stars near Sagittarius A star called S2 as it made its closest approach to the black hole. They measured the star's position with incredible precision, and they found that its orbit was precessing exactly as general relativity predicted. This was a triumph for physics, confirmation that Einstein's theory holds true even in the most extreme conditions. But the galactic center holds more secrets. There are objects near the black hole that do not behave like normal stars. Some of these objects appear to be clouds of gas, but they move on orbits that suggest they are more than just gas. They may be stars surrounded by thick envelopes of gas, or they may be something entirely different. No one knows for certain. One of these objects, called G2, was observed approaching the black hole in 2013. Astronomers predicted that the black hole's gravity would tear the cloud apart, potentially feeding the black hole and causing a burst of activity. But when G2 reached its closest point to the black hole, nothing happened. The cloud passed by unharmed, its structure intact. This suggested that G2 was not just a cloud of gas. It may have been a star hidden within the gas, or it may have been something else entirely. The galactic center is a place of extremes. It is a place where gravity is so strong it warps space and time. It is a place where stars orbit at thousands of kilometers per second. It is a place where the rules of physics are pushed to their limits, and it is a place that holds many secrets we have not yet uncovered. The Milky Way is a spiral galaxy, which means it has long, curved arms extending outward from the center. These arms are not solid structures. They are not made of any particular material. They are density waves, regions where stars and gas are more densely packed than in the space between the arms. Imagine a traffic jam on a highway. Cars slow down and bunch together in the jam, then speed up and spread out once they pass through. The traffic jam itself does not move down the highway. It stays in place, even as individual cars move through it. The spiral arms of the Milky Way work in a similar way. Stars and gas move through the arms, slowing down as they enter and speeding up as they leave. The arms themselves remain in place, rotating slowly around the galaxy. The Milky Way has 4 major spiral arms. They are called the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm. Our Sun is located in a smaller structure called the Orion Spur, a minor arm that branches off from the Sagittarius arm. We are about halfway out from the centre of the galaxy, in a relatively quiet region far from the dense star-forming areas of the major arms. The spiral arms are some of the most active regions in the galaxy. This is where new stars are born. The density waves compress clouds of gas and dust as they pass through the arms, triggering the collapse of the clouds and the formation of new stars. These newborn stars are hot and bright, shining with intense blue and white light. They illuminate the gas around them, creating glowing regions called H2 regions, some of the most beautiful structures in the galaxy. But the spiral arms are also dangerous places. The dense concentration of stars and gas means that collisions are more likely. Stars can pass close to each other, disrupting planetary systems and flinging planets out into interstellar space. Supernovae, the explosive deaths of massive stars, are more common in the spiral arms, releasing bursts of radiation that can sterilize nearby planets. Our position in the Orion Spur, far from the major spiral arms, may be one of the reasons life was able to develop on Earth. We're in a relatively safe region of the galaxy, far from the chaos and danger of the spiral arms, but even here, we're not entirely safe. Every 200 million years, as the Sun orbits the galaxy, we pass through one of the major spiral arms. During these passages, the risk of nearby supernova and close encounters with other stars increases. Some scientists have suggested that these passages may be linked to mass extinction events on Earth, though the evidence is still uncertain. The spiral arms are not permanent structures. They evolve over time, changing shape and position as the galaxy rotates. In some regions, the arms split or merge. In others, they fade away entirely. The Milky Way's spiral structure is constantly shifting, a dynamic pattern that changes on timescales of millions of years. One of the great mysteries of spiral galaxies is how the spiral arms form in the first place. Astronomers have proposed several theories, but none can fully explain all the features we observe. The most widely accepted theory is that the arms are created by density waves, disturbances in the gravitational field of the galaxy that propagate through the disk like ripples on a pond. But the origin of these density waves is still debated. Some scientists believe the density waves are created by interactions with other galaxies. When a small galaxy passes close to a larger one, its gravity can create ripples that propagate through the larger galaxy's disk, forming spiral arms. Others believe the spiral arms are created by instabilities within the galaxy itself, as regions of slightly higher density attract more matter and grow over time. The spiral arms are also closely linked to the bar at the centre of the galaxy. The bar rotates at a different speed than the rest of the galaxy, and this difference in rotation speed creates the spiral pattern. As the bar sweeps through the galaxy, it pulls stars and gas along with it, creating the arms. But the relationship between the bar and the arms is complex. The bar can strengthen the spiral arms, making them more prominent, but the spiral arms can also feed back on the bar, changing its shape and rotation. The two structures are locked in a delicate dance, each influencing the other in ways we're only beginning to understand. The spiral arms are one of the defining features of the Milky Way. They give the galaxy its characteristic shape, and they are the birthplaces of new stars. But they are also some of the most mysterious structures in the galaxy, and many questions about them remain unanswered. Surrounding the Milky Way, far above and below the galactic disk, there is a vast spherical region called the halo. The halo is home to the oldest stars in the galaxy, stars that formed more than 13 billion years ago, in the first billion years after the Big Bang. These stars are different from the stars in the disk. They are metal poor, meaning they contain very little in the way of elements heavier than hydrogen and helium. This is because they formed before the universe had been enriched with heavy elements by the deaths of earlier generations of stars. They are relics of a simpler time, when the universe was young and the first stars were just beginning to light up the darkness. The halo stars orbit the galaxy on long elliptical paths that take them far above and below the disk. They do not follow the orderly rotation of the disk stars. Instead, they move on chaotic, randomly oriented orbits, plunging through the disk and then soaring back out into the halo. This random motion is evidence that the halo formed in a different way than the disk. Astronomers believe the halo was formed by the mergers of smaller galaxies with the Milky Way. In the early universe, galaxies were smaller and more numerous. Over billions of years, these smaller galaxies collided and merged, forming larger galaxies like the Milky Way. The stars from these smaller galaxies were scattered into the halo, where they continue to orbit to this day. The halo also contains globular clusters, dense spherical collections of hundreds of thousands of stars. Globular clusters are some of the oldest structures in the galaxy, with ages ranging from 10 to 13 billion years. They orbit the galaxy on long, slow paths, passing through the disk every few hundred million years. Each globular cluster is a miniature galaxy, a self-contained system of stars held together by gravity. The stars in a globular cluster are packed so tightly that they interact with each other frequently, exchanging energy and sometimes colliding. These interactions can lead to the formation of exotic objects like blue stragglers, stars that appear younger than they should be, and millisecond pulsars rapidly spinning neutron stars. The halo is also home to streams of stars, long ribbons of stars that wrap around the galaxy. These streams are the remnants of smaller galaxies and globular clusters that were torn apart by the Milky Way's gravity. As these objects fell toward the galaxy, they were stretched and pulled, their stars scattered into long lines that now orbit the galaxy like cosmic threads. One of the most prominent of these streams is the Sagittarius stream, formed from the Sagittarius dwarf elliptical galaxy. This small galaxy is currently being torn apart by the Milky Way, and its stars are being scattered into a stream that wraps around the galaxy multiple times. Observations of the Sagittarius stream have provided valuable insights into the structure and mass of the Milky Way, as well as the properties of dark matter. The halo is a quiet, sparse region of the galaxy. The stars here are few and far between, separated by vast distances. The halo does not glow with the light of young, bright stars. It is dark, ancient, a relic of the galaxy's violent past. But the halo is not entirely empty. There is evidence that the halo contains vast amounts of hot gas, heated to millions of degrees. This gas is so hot it emits X-rays, though the emission is faint and difficult to detect. The origin of this hot gas is uncertain. It may be gas that was heated by supernova explosions and blown out of the disk, or it may be gas that was stripped from smaller galaxies as they merged with the Milky Way. The halo is also the domain of dark matter. The dark matter halo extends far beyond the visible stars, reaching out into intergalactic space. It is the dark matter halo that holds the galaxy together, providing the gravitational pull that keeps the stars in orbit. Without the dark matter halo, the Milky Way would not exist. Studying the halo is like studying the fossil record of the galaxy. The stars in the halo are the oldest in the galaxy, and they carry with them the chemical signatures of the early universe. By analysing the light from these stars, astronomers can learn about the conditions in the universe billions of years ago, when the first stars were forming and the first galaxies were taking shape. The halo is a reminder that the Milky Way has a long and complex history. It is not a single, unchanging structure. It is the product of billions of years of growth, shaped by countless mergers and interactions with other galaxies, and it is still changing, still growing, as it continues to consume smaller galaxies and add their stars to its halo. The Milky Way is more than what we can see. The stars, the gas, the dust, all of the visible matter in the galaxy makes up only a small fraction of the galaxy's total mass. The rest is dark matter, an invisible substance that does not emit, absorb, or reflect light. We cannot see it, we cannot touch it, but we know it is there because of its gravitational effects. Dark matter was first proposed in the 1930s by the astronomer Fritz Zwicky. He was studying clusters of galaxies and noticed that the galaxies within the clusters were moving faster than they should be. According to the laws of gravity, the visible matter in the clusters was not enough to hold them together. The galaxies should have flown apart, but they did not. Zwicky concluded that there must be additional matter in the clusters, matter that was invisible but massive enough to provide the extra gravitational pull needed to hold the clusters together. For decades, Zwicky's idea was largely ignored. It was only in the 1970s, when the astronomer Vera Rubin studied the rotation of galaxies, that dark matter became widely accepted. Rubin measured the rotation speeds of stars in spiral galaxies and found that stars in the outer regions of galaxies were moving just as fast as stars near the centre. This was unexpected. According to the laws of gravity, stars farther from the centre should move more slowly, but they did not. The only way to explain this observation was to assume that galaxies are surrounded by vast halos of invisible matter. This dark matter provides additional gravitational pull, keeping the outer stars moving faster than they would otherwise. Rubin's observations were the first strong evidence that dark matter is real, and that it plays a crucial role in the structure of galaxies. In the Milky Way, dark matter makes up about 85% of the galaxy's total mass. The dark matter halo extends far beyond the visible edges of the galaxy, reaching out to distances of several 100,000 light-years. It is this halo that holds the galaxy together, providing the gravitational framework upon which the visible matter is arranged. But what is dark matter? This is one of the greatest unsolved mysteries in physics. We do not know what dark matter is made of. We do not know how it formed. We do not even know if it is made of particles at all. The leading hypothesis is that dark matter is made of a new type of particle, a particle that does not interact with light or ordinary matter except through gravity. Several candidates have been proposed, including WIMPs, weakly interacting massive particles, and axions. Scientists have built sensitive detectors deep underground, shielded from cosmic rays and other sources of interference, in the hope of detecting these particles. So far, no dark matter particle has been detected. An alternative hypothesis is that dark matter does not exist at all, and that the observations we attribute to dark matter are actually due to a modification of the laws of gravity. This idea, called modified Newtonian dynamics, or MOND, proposes that gravity behaves differently on very large scales than it does in our solar system. MOND can explain some of the observations of galaxy rotation, but it struggles to explain other phenomena such as the behavior of galaxy clusters and the cosmic microwave background radiation. Most physicists believe that dark matter is real and that it is made of some type of particle. The search for dark matter particles is one of the most active areas of research in physics. Experiments are being conducted all over the world using a variety of techniques in the hope of finally detecting a dark matter particle and solving one of the greatest mysteries of the universe. In the Milky Way, the dark matter halo is not uniform. It is clumpier in some regions than in others. These clumps are the remnants of smaller dark matter halos that merged with the Milky Way billions of years ago. As the Milky Way consumed smaller galaxies, it also absorbed their dark matter halos, adding to its own. Some of these dark matter clumps may still contain stars. There are predictions that there could be small, dark galaxies orbiting the Milky Way, galaxies that are made almost entirely of dark matter with only a handful of visible stars. These dark galaxies would be extremely difficult to detect, but their gravitational effects on nearby stars could give them away. Dark matter is essential to the structure and evolution of the Milky Way. Without dark matter, the galaxy would not have formed. The early universe was filled with a nearly uniform distribution of gas. The tiny density fluctuations that existed were too small to collapse under their own gravity. But dark matter, which does not interact with light, could begin collapsing earlier, creating gravitational wells that attracted ordinary matter. The first galaxies formed in these dark matter halos, and the Milky Way is the result of billions of years of growth within its dark matter halo. Dark matter is the hidden skeleton of the galaxy. It is the invisible framework that holds everything together. And yet, despite its importance, we know almost nothing about it. It is a secret hidden in plain sight, a mystery that continues to elude us. The Milky Way is a place of constant creation. Every year, a few new stars are born in the galaxy, emerging from vast clouds of gas and dust scattered throughout the galactic disk. These clouds, called molecular clouds, are the nurseries of stars, the places where the raw materials of the universe are transformed into shining suns. Molecular clouds are cold, dark, and dense. They are made mostly of hydrogen, the simplest and most abundant element in the universe, along with traces of helium and heavier elements. The clouds are so dense that they block out the light from stars behind them, appearing as dark patches in the sky. But within these dark clouds, something extraordinary is happening. Gravity is always at work, pulling the gas in the cloud together. In most cases, the cloud is stable. The pressure of the gas pushing outward balances the pull of gravity pulling inward. But sometimes, something disturbs the cloud. It could be the shock wave from a nearby supernova, the pressure wave from a passing spiral arm, or the collision of two clouds. Whatever the cause, the disturbance compresses part of the cloud, increasing its density. Once the density increases past a certain threshold, gravity takes over. The compressed region begins to collapse, pulling more and more gas inward. As the gas collapses, it heats up, and the center of the collapsing region becomes a protostar, a hot, dense core that will eventually become a star. The protostar continues to grow, pulling in more gas from the surrounding cloud. As it grows, it heats up. The temperature at the center rises, reaching millions of degrees. At these temperatures, nuclear fusion begins. Hydrogen atoms are fused together to form helium, releasing enormous amounts of energy. The protostar becomes a true star, shining with its own light. But the birth of a star is not a gentle process. The collapsing cloud does not fall straight inward. It has some rotation, and as it collapses, the rotation speeds up, just like a figure skater spinning faster as they pull their arms in. This rotation causes the gas to form a disk around the protostar called a protoplanetary disk. The protoplanetary disk is where planets are born. Over millions of years, the gas and dust in the disk clump together, forming larger and larger objects. These objects collide and merge, growing into asteroids, then into planetesimals, and eventually into planets. The protostar at the center of the disk becomes a fully fledged star, and the disk around it becomes a planetary system. Not all stars form alone. In fact, most stars form in clusters, groups of hundreds or thousands of stars born from the same molecular cloud. These star clusters are chaotic, crowded places. The stars are so close together that they interact with each other, exchanging energy and sometimes colliding. Over time, most star clusters disperse, their stars drifting apart and spreading throughout the galaxy. But some clusters remain bound together by gravity, becoming open clusters that can survive for billions of years. The Milky Way contains thousands of these open clusters, scattered throughout the galactic disk. Some are young, just a few million years old, still glowing with the light of hot blue stars. Others are old, billions of years old, their stars dimmed and reddened with age. The rate of star formation in the Milky Way has varied over time. In the early universe, when the galaxy was young and gas was abundant, star formation was rapid. Billions of stars formed in a relatively short time, lighting up the galaxy. But over billions of years, the gas has been depleted. Much of it has been turned into stars. Some of it has been blown out of the galaxy by supernova explosions and stellar winds. The rate of star formation has slowed. Today, the Milky Way forms only a few new stars per year. This is much slower than in the past, but it is still enough to keep the galaxy vibrant and alive. The young, hot stars that form today illuminate the gas clouds around them, creating glowing nebulae that are some of the most beautiful objects in the night sky. One of the most famous of these nebulae is the Orion Nebula, a vast cloud of gas and dust located about 1,500 light-years from Earth. The Orion Nebula is a stellar nursery, a place where new stars are being born right now. Thousands of young stars light up the nebula from within, their intense ultraviolet light causing the gas to glow in brilliant shades of red, green, and blue. Studying star-forming regions like the Orion Nebula has given astronomers deep insights into how stars and planets form. We now know that planet formation is a natural byproduct of star formation. Nearly every star has a protoplanetary disk, and nearly every disk can form planets. This means that planetary systems are common in the galaxy, and the potential for life is widespread. But star formation is not a purely creative process. It is also destructive. The massive stars that form in molecular clouds live fast and die young. They burn through their nuclear fuel in just a few million years, then explode as supernovae, releasing shock waves that tear through the surrounding gas. These shock waves can trigger new rounds of star formation, compressing nearby clouds and starting the cycle anew. But they can also disrupt star-forming regions, blowing gas away and preventing new stars from forming. The balance between creation and destruction shapes the evolution of the galaxy. Star formation creates new stars and enriches the galaxy with heavy elements. But supernova explosions blow gas out of the galaxy, reducing the material available for future star formation. Over billions of years, this cycle has slowed, and the Milky Way is now in a more sedate phase of its life. But star formation has not stopped. It continues, slowly and steadily, in pockets scattered throughout the galaxy. And as long as there is gas, as long as there are clouds dense enough to collapse, new stars will continue to be born. Stars do not live forever. They are born, they live for billions of years, and eventually they die. The way a star dies depends on its mass. Small stars die gently. Massive stars die violently. But all stars, no matter their size, return their material to the galaxy, enriching the interstellar medium with the elements they created during their lives. The smallest stars, called red dwarfs, are the most common type of star in the galaxy. Red dwarfs are tiny, with masses less than half that of the Sun. They burn their nuclear fuel very slowly, shining dimly for trillions of years. A red dwarf born today will still be shining long after the Sun has died, long after the Milky Way has merged with Andromeda, long after most of the stars in the universe have burned out. But even red dwarfs will eventually run out of fuel. When they do, they will simply fade away, becoming dim, cooling embers called white dwarfs. White dwarfs are the remnants of stars, dense cores of carbon and oxygen left behind after the outer layers have been shed. They no longer produce energy through nuclear fusion. They simply glow with the residual heat left over from their active days, slowly cooling over billions of years until they become black dwarfs, cold and dark. Stars like the Sun have more dramatic endings. When the Sun runs out of hydrogen in its core, about 5 billion years from now, it will begin to die. The core will contract, heating up and causing the outer layers to expand. The Sun will become a red giant, a vast, bloated star hundreds of times larger than it is now. The outer layers will extend past the orbit of Earth, engulfing the inner planets, and possibly Earth itself. For a few 100 million years, the Sun will burn helium in its core, fusing it into carbon and oxygen. But eventually the helium will run out. The core will contract again, and the outer layers will be blown off into space, forming a beautiful shell of glowing gas called a planetary nebula. At the centre of the nebula, the Sun's core will remain, now a white dwarf, slowly cooling over billions of years. This is the fate of most stars in the galaxy. They live for billions of years, then shed their outer layers and fade away as white dwarfs. But for the most massive stars, death is far more violent. Massive stars, those with masses more than 8 times that of the Sun, live fast and die young. They burn through their nuclear fuel in just a few million years. During their lives, they fuse hydrogen into helium, helium into carbon, carbon into oxygen, oxygen into silicon, and finally silicon into iron. Each stage of fusion produces energy, supporting the star against gravitational collapse. But iron is different. Iron cannot be fused to produce energy. When a massive star's core turns to iron, it can no longer support itself. The core collapses in a fraction of a second, and the collapse releases an enormous amount of energy. This energy blows the outer layers of the star apart in a supernova explosion, one of the most powerful events in the universe. For a few weeks, a supernova can outshine an entire galaxy. The explosion releases as much energy in a few seconds as the Sun will release in its entire 10 billion year lifetime. The shock wave from the explosion tears through space, heating gas to millions of degrees and compressing clouds to trigger new rounds of star formation. But supernovae do more than just destroy. They also create. During the explosion, the intense heat and pressure create new elements, elements that cannot be formed inside stars. Gold, platinum, uranium, all of these elements are created in supernova explosions. When the explosion tears through space, it scatters these elements into the interstellar medium, enriching the gas from which future stars and planets will form. Every atom of gold in a wedding ring, every atom of uranium in a nuclear reactor, every atom of iron in your blood. All of these atoms were created in a supernova explosion billions of years ago. We are made of stardust. the remnants of stars that died long before the Sun was born. After a supernova, what remains of the star's core depends on its mass. If the core is less than about 3 times the mass of the Sun, it will become a neutron star, a tiny, incredibly dense object made entirely of neutrons. Neutron stars are only about 20 kilometers across, but they contain more mass than the Sun. A teaspoon of neutron star material would weigh 1 billion tons. Neutron stars are also incredibly magnetic. Some neutron stars, called pulsars, emit beams of radiation from their magnetic poles. As the neutron star rotates, these beams sweep across space like lighthouse beams. If one of the beams points toward Earth, we see a pulse of radiation every time the neutron star rotates. Some pulsars spin hundreds of times per second, faster than a kitchen blender. If the core of the star is more than about 3 times the mass of the Sun, even the pressure of neutrons cannot support it. The core collapses completely, becoming a black hole, a region of space where gravity is so strong that nothing can escape, not even light. Black holes are the ultimate endpoint of stellar evolution. They are the graves of the most massive stars, regions of space where the laws of physics break down and time itself comes to a stop. But black holes are not entirely black. They emit a faint glow called Hawking radiation, predicted by the physicist Stephen Hawking. Over unimaginably long timescales, black holes slowly evaporate, losing mass until they vanish entirely. The deaths of stars are essential to the life cycle of the galaxy. Stars create heavy elements through nuclear fusion, and supernovae scatter these elements into space. Over billions of years, the interstellar medium becomes enriched with heavy elements, and each new generation of stars is born with a slightly higher abundance of these elements. The Sun, for example, contains about 2% heavy elements, all of which were created in previous generations of stars. This process of enrichment has been going on for billions of years. The first stars in the universe, called Population 3 stars, contain no heavy elements at all. They were made purely of hydrogen and helium left over from the Big Bang. When these stars died, they enriched the interstellar medium with the first heavy elements, making it possible for the next generation of stars to form planets, and eventually, life. We owe our existence to the deaths of stars. Without supernovae, there would be no carbon, no oxygen, no iron. There would be no planets, no oceans, no life. The universe would be a cold, dark place, filled only with hydrogen and helium. But because stars die, because they return their material to the galaxy, the universe is rich and complex, filled with the ingredients for life. The Milky Way is threaded with invisible lines of force. These lines are magnetic fields, created by the motion of charged particles and electric currents flowing through the galaxy. We cannot see these fields with our eyes, but they are there, shaping the behavior of gas, dust, and cosmic rays, and influencing the structure of the galaxy itself. Magnetic fields in the Milky Way are weak compared to the magnetic fields we encounter in everyday life. A typical refrigerator magnet has a magnetic field strength of about 100 Gauss. The magnetic field in the Milky Way is about 1 million times weaker, only a few microgauss. But despite their weakness, these magnetic fields play a crucial role in the galaxy. The magnetic fields are generated by the motion of gas in the galactic disk. The galaxy rotates, and this rotation causes the gas to move in circular patterns. As the gas moves, it carries electric currents with it, and these currents generate magnetic fields. The magnetic fields, in turn, affect the motion of the gas, creating a complex feedback loop. The magnetic fields in the Milky Way are not uniform. They are tangled and twisted, with different regions having different field strengths and orientations. In some regions, the magnetic field lines run parallel to the spiral arms. In other regions, they run perpendicular to the arms. The exact structure of the magnetic field is still not fully understood. One of the ways astronomers study the magnetic field is by observing polarized light. When light passes through a magnetic field, its polarization is affected. By measuring the polarization of a light from distant stars, astronomers can infer the strength and direction of the magnetic field between us and the star. Another way to study the magnetic field is by observing cosmic rays. Cosmic rays are high-energy particles, mostly protons, that travel through the galaxy at nearly the speed of light. These particles are charged, and they are affected by magnetic fields. The magnetic fields cause the cosmic rays to spiral along the field lines, trapping them in the galaxy and preventing them from escaping into intergalactic space. Cosmic rays play an important role in the galaxy. They carry energy, and when they collide with gas in the interstellar medium, they heat the gas and ionize it, creating a warm, diffuse component of the interstellar medium. Cosmic rays also influence star formation. In dense molecular clouds, cosmic rays can ionize the gas, affecting the chemistry of the cloud and the rate at which it collapses to form stars. The origin of cosmic rays is still a mystery. Most cosmic rays are thought to be produced by supernova explosions. When a massive star explodes, the shock wave from the explosion accelerates particles to incredibly high energies, turning them into cosmic rays. But some cosmic rays have energies far higher than can be explained by supernovae. The origin of these ultra-high energy cosmic rays is unknown. They may come from supermassive black holes, from colliding neutron stars, or from some other, unknown source. The magnetic field also plays a role in the formation of stars. When a cloud of gas collapses to form a star, the magnetic field threads through the cloud. As the cloud collapses, the magnetic field is compressed and strengthened. The magnetic field can slow down the collapse, preventing the cloud from forming a star too quickly. It can also channel material onto the forming star, creating jets of gas that shoot out from the poles of the protostar. These jets are one of the most dramatic features of star formation. They are narrow streams of gas moving at hundreds of kilometers per second, driven by the magnetic field and the rotation of the collapsing cloud. The jets can extend for light years, carving out cavities in the surrounding gas and triggering shock waves that heat the gas to thousands of degrees. Observations of these jets have provided crucial insights into the role of magnetic fields in star formation. The magnetic field also affects the structure of the interstellar medium. The interstellar medium is not uniform. It consists of several components with different temperatures and densities. There is cold, dense gas in molecular clouds. There is warm, diffuse gas in the space between clouds. And there is hot, ionized gas in regions heated by supernova explosions and stellar winds. The magnetic field helps to maintain the structure of the interstellar medium. It provides pressure that supports the gas against gravitational collapse. It also inhibits the mixing of different components of the interstellar medium, keeping the cold gas separate from the hot gas. But the magnetic field is not just passive, it is dynamic, constantly changing in response to the motion of the gas and the forces acting on it. Magnetic reconnection, a process where magnetic field lines break and reconnect, can release large amounts of energy, heating the gas and accelerating particles. This process is similar to what happens in solar flares on the Sun, but on a much larger scale. The magnetic field in the Milky Way is a hidden force, invisible and intangible, but essential to the structure and evolution of the galaxy. It shapes the interstellar medium, influences star formation, and traps cosmic rays. And yet, despite decades of study, many aspects of the galactic magnetic field remain mysterious. Its origin, its structure, and its evolution are still not fully understood. The Milky Way does not travel alone through space. It is surrounded by a swarm of smaller galaxies, called satellite galaxies, that orbit our galaxy like moons orbiting a planet. These satellite galaxies are the remnants of the early universe, small collections of stars that formed billions of years ago and have been held in the Milky Way's gravitational embrace ever since. The two largest and most famous satellite galaxies are the Large Magellanic Cloud and the Small Magellanic Cloud. These two galaxies are visible to the naked eye from the southern hemisphere, appearing as faint, fuzzy patches of light in the night sky. They are named after the explorer Ferdinand Magellan, who observed them during his voyage around the world in the 16th century. The Large Magellanic Cloud is about 160,000 light-years from Earth. It contains about 30 billion stars, making it much smaller than the Milky Way, which contains between 200 and 400 billion stars. Despite its small size, the Large Magellanic Cloud is actively forming stars, with several large star-forming regions visible within it. One of the most famous features of the Large Magellanic Cloud is the Tarantula Nebula, a massive star-forming region that is one of the largest and most active in the local universe. The Tarantula Nebula contains thousands of young hot stars, including some of the most massive stars ever discovered. These stars are so massive and so bright that they would be visible from Earth even if they were located in a distant galaxy millions of light-years away. The Small Magellanic Cloud is even smaller, containing only about 3 billion stars. It is about 200,000 light-years from Earth. Like the Large Magellanic Cloud, it is actively forming stars, and it has a rich population of young blue stars. Both Magellanic Clouds are being torn apart by the gravity of the Milky Way. As they orbit our galaxy, the tidal forces from the Milky Way are pulling stars and gas out of the Magellanic Clouds, creating long streams of material called the Magellanic Stream and the leading arm. These streams wrap around the Milky Way, trailing behind and leading ahead of the Magellanic Clouds as they orbit. The Magellanic Stream is one of the largest structures in the sky. It stretches for more than 600,000 light-years, longer than the diameter of the Milky Way itself. It contains vast amounts of gas, enough to form billions of new stars. As this gas falls into the Milky Way, it will fuel future episodes of star formation, adding to the galaxy's stellar population. But the Magellanic Clouds are not the only satellites of the Milky Way. There are dozens of smaller satellite galaxies orbiting our galaxy, most of them so faint that they can only be detected with large telescopes. These small galaxies are called dwarf galaxies, and they contain only a few million stars each, far fewer than the Milky Way. One of the closest dwarf galaxies is the Sagittarius dwarf elliptical galaxy, located only about 70,000 light-years from Earth. This galaxy is being torn apart by the Milky Way's gravity, and its stars are being scattered into long streams that wrap around our galaxy. The Sagittarius dwarf elliptical galaxy is one of several satellite galaxies that are in the process of merging with the Milky Way. These mergers are a natural part of the life of a galaxy. In the early universe, galaxies grew by merging with smaller galaxies. The Milky Way has consumed dozens, perhaps hundreds, of smaller galaxies over its lifetime, adding their stars to its halo and disk. This process is still ongoing. The Milky Way is still consuming satellite galaxies, and it will continue to do so for billions of years. The satellite galaxies are not just interesting in their own right, they also provide crucial clues about the dark matter halo of the Milky Way. The orbits of the satellite galaxies are determined by the gravitational pull of the Milky Way, and by studying these orbits, astronomers can map the distribution of dark matter in the galaxy. But there is a puzzle. According to simulations of galaxy formation, the Milky Way should have far more satellite galaxies than we observe. These simulations predict that there should be hundreds of small dark matter halos orbiting the Milky Way, each potentially containing a small dwarf galaxy. But we only observe a few dozen satellite galaxies. This discrepancy is known as the missing satellites problem. There are several possible explanations for the missing satellites. One possibility is that many of the small dark matter halos do not contain stars. If the halos are too small, or if the gas within them was blown away by supernova explosions or the intense radiation from the first stars, then no stars would have formed, and the halos would be invisible to us. Another possibility is that the missing satellites are there, but they are too faint for us to see. Modern surveys are discovering new dwarf galaxies all the time, some of them so faint that they contain only a few hundred stars. It may be that with deeper surveys and better telescopes, we will eventually find the missing satellites. The satellite galaxies are also laboratories for studying dark matter. Because dwarf galaxies are so small and so dominated by dark matter, they are ideal places to search for dark matter particles. If dark matter particles decay or annihilate, they could produce detectable signals such as gamma rays or X-rays, and these signals would be strongest in regions with high concentrations of dark matter, such as dwarf galaxies. Several experiments are searching for these signals, looking for excess gamma rays or X-rays coming from dwarf galaxies. So far, no clear detection of dark matter has been made, but the search continues. The satellite galaxies are the Milky Way's companions, orbiting our galaxy and slowly being consumed by its gravity. They are the remnants of the early universe, small collections of stars that have survived for billions of years, and they are a reminder that the Milky Way is not isolated. It is part of a larger cosmic ecosystem, interacting with and shaping the smaller galaxies around it. The Milky Way and the Andromeda galaxy are on a collision course. Right now, Andromeda is 2.5 million light-years away, moving toward us at about 110 kilometers per second. In about 4 billion years, the two galaxies will collide, merging to form a single larger galaxy. This collision will be one of the most dramatic events in the history of the Milky Way. But it will not be a violent crash. Galaxies are mostly empty space. The stars in the two galaxies are so far apart that the chances of two stars actually colliding are extremely small. Instead, the collision will be a slow, graceful dance as the two galaxies pass through each other, their gravity pulling and stretching them into new shapes. The first encounter will happen when the outer edges of the two galaxies begin to overlap. The gravitational pull from Andromeda will start to distort the Milky Way, pulling stars and gas out of the disk and flinging them into space. Long tidal tails will form, streams of stars stretching out from both galaxies as they interact. As the two galaxies pass through each other, their gas clouds will collide. Unlike the stars, the gas clouds are not empty space. They will crash into each other, compressing and heating, triggering enormous bursts of star formation. New stars will light up both galaxies, and the combined system will glow brightly in the infrared and ultraviolet, a signal that will be visible across the universe. After the first pass, the two galaxies will separate, moving apart under the momentum of their approach, but gravity will not let them go. The gravitational pull between the two galaxies will slow them down, pulling them back together for a second collision, and then a third. Each collision will be more violent than the last, as the two galaxies lose energy and spiral closer together. Eventually, after several collisions over the course of 1 billion years, the two galaxies will merge completely. Their stars will be mixed together, and their supermassive black holes will sink to the center of the merged galaxy, eventually merging into a single, even more massive black hole. The merged galaxy will no longer be a spiral. The collisions will have disrupted the delicate structure of the spiral arms, scrambling the stars into a more chaotic elliptical shape. The new galaxy will be an elliptical galaxy, a smooth, featureless collection of stars with no spiral arms, no disk, and no ongoing star formation. Astronomers have already given this future galaxy a name, Milkomeda, a combination of Milky Way and Andromeda. What will happen to the Sun and the solar system during this collision? Most likely, nothing dramatic. The chances of the Sun colliding with another star are incredibly small. But the Sun's orbit around the galaxy will change. It may be flung out into the outer regions of the merged galaxy, or it may be pulled into the crowded central regions. Either way, the Sun will continue to shine, and the planets will continue to orbit, largely unaffected by the chaos around them. But there is one concern. The merger will trigger enormous bursts of star formation, and with new star formation comes new supernova explosions. If a supernova explodes too close to the solar system, the intense radiation could strip away Earth's ozone layer, exposing the surface to harmful ultraviolet radiation and potentially causing a mass extinction. However, the chances of this happening are small. Space is vast, and even in the crowded conditions of a merging galaxy, the distances between stars are enormous. The Sun will most likely pass through the merger unscathed. But the merger with Andromeda is not the only future collision the Milky Way faces. There are several other large galaxies in the local group, and over the next few billion years, many of them will also merge with the Milky Way. The Triangulum galaxy, the third largest member of the local group, may merge with the Milky Way or with Andromeda in the distant future. These mergers are a natural part of the life cycle of galaxies. In the early universe, galaxies grew by merging with each other. The Milky Way itself is the product of countless mergers, each one adding mass and reshaping the galaxy. And this process will continue into the future as the Milky Way continues to grow and evolve. The collision with Andromeda is still 4 billion years away. By that time, the Sun will be near the end of its life. It will be a red giant, its outer layers swollen and bloated, possibly engulfing the inner planets. Life on Earth, if it still exists, will have had to adapt to dramatic changes in the Sun's output. But for now, the Milky Way and Andromeda remain separate, two majestic spiral galaxies slowly drifting toward each other through the void. The collision is inevitable, written into the fabric of space-time by the laws of gravity, and when it happens, it will reshape the cosmos on a scale almost beyond imagination. For centuries, astronomers believed that the Milky Way's disk was flat, a perfect plane of stars and gas extending outward from the centre. But recent observations have revealed a startling truth. The disk is not flat. It is warped, twisted like the brim of a hat, rising on one side and dipping on the other. This warp is subtle. If you could look at the Milky Way from the side from a great distance, you would see that the disk curves gently upward on one edge and downward on the other. The warp extends throughout the outer regions of the galaxy, affecting hundreds of billions of stars. The discovery of the warp came from careful measurements of the distances to stars in the outer disk. By plotting the three-dimensional positions of these stars, astronomers were able to map the shape of the disk. What they found was unexpected. Instead of a flat plane, the disk curves and twists, with the northern edge rising above the plane and the southern edge dipping below it. The warp is not uniform. It changes as you move around the galaxy. In some regions, the warp is more pronounced. In others, it is barely noticeable. The structure is dynamic, shifting over millions of years as the galaxy rotates and evolves. What causes the warp? This is one of the mysteries that astronomers are still working to solve. There are several theories. One possibility is that the warp is caused by the gravitational pull of the Magellanic Clouds. These two satellite galaxies are massive enough to exert a significant gravitational force on the Milky Way. As they orbit our galaxy, their gravity tugs on the outer disk, pulling it out of alignment and creating the warp. Another possibility is that the warp is caused by the distribution of dark matter around the galaxy. If the dark matter halo is not perfectly spherical, if it has an asymmetric shape, it could create gravitational forces that twist the disk. Computer simulations have shown that even small asymmetries in the dark matter halo can produce warps similar to what we observe in the Milky Way. A third possibility is that the warp is a relic of a past collision. Billions of years ago, the Milky Way may have collided with a smaller galaxy. The collision would have sent shockwaves through the disk, distorting its shape. Even though the collision happened long ago, the warp it created could still be visible today, slowly fading over billions of years. The warp is not unique to the Milky Way. Many spiral galaxies have warped disks. In fact, warps are so common that they may be a normal feature of spiral galaxies. This suggests that the forces that create warps are a natural part of galaxy evolution. Studying the warp is important because it gives us insights into the forces acting on the galaxy. By measuring the shape and motion of the warp, astronomers can learn about the distribution of mass in the Milky Way, both visible and dark. The warp is a diagnostic tool, a way to probe the hidden structure of the galaxy. The warp also affects the motion of stars and gas in the outer disk. Stars moving through the warped region experience forces that change their orbits, nudging them up or down out of the plane. Gas clouds moving through the warp are compressed and stretched, which can trigger or suppress star formation. The outer regions of the Milky Way, where the warp is most pronounced, are some of the least explored parts of the galaxy. These regions are far from the bright centre, far from the densest concentrations of stars. They are quiet, sparsely populated regions where stars are few and far between. But even in these distant regions, there are surprises. Astronomers have discovered young star clusters in the outer disk, far from the spiral arms where most star formation occurs. These clusters are puzzling. They should not be there. Star formation in the outer disk should be rare, because the gas is thin and diffuse. But the presence of these clusters suggests that star formation is more complex than we thought, influenced by factors we do not yet fully understand. The warp is a reminder that the Milky Way is not a static, unchanging structure. It is a dynamic, living system, constantly evolving in response to the forces acting on it. The galaxy is shaped by gravity, by dark matter, by collisions with other galaxies, and by the internal processes of star formation and death. And the warp is a visible manifestation of these forces, a twist in the fabric of the galaxy that tells a story of interactions and influences stretching back billions of years. Above and below the disk of the Milky Way, at distances of several thousand light years, there is a phenomenon known as the galactic fountain. This fountain is not made of water. It is made of gas, hot gas that has been blown out of the disk by supernova explosions and stellar winds. Massive stars live fast and die violently. When they explode as supernovae, they release enormous amounts of energy. This energy heats the surrounding gas to millions of degrees, creating expanding bubbles of hot, ionized gas. These bubbles rise out of the galactic disk, driven by their own buoyancy, like bubbles rising in water. As the hot gas rises, it cools and slows down. Eventually it reaches a maximum height, several thousand light-years above the disk. Then, pulled by the gravity of the galaxy, it falls back down, raining back onto the disk like a fountain. This cycle of gas being blown out of the disk and falling back down is called the galactic fountain. The galactic fountain plays an important role in the life cycle of the galaxy. It transports gas from the disk to the halo and back again. It mixes gas from different regions of the galaxy, spreading heavy elements created by supernova throughout the disk, and it regulates star formation, removing gas from star-forming regions and slowing the rate at which new stars are born. The fountain also enriches the halo with heavy elements. As the hot gas rises out of the disk, it carries with it the metals created by dying stars. Some of this gas escapes the galaxy entirely, blown out into intergalactic space by the force of the supernova explosions. But much of it falls back down, enriching the disk with heavy elements and making it possible for future generations of stars to form planets and potentially life. Observations of the galactic fountain are difficult. The hot gas emits X-rays and ultraviolet light, which are absorbed by Earth's atmosphere. To observe the fountain, astronomers must use space-based telescopes, such as the Hubble Space Telescope and the Chandra X-ray Observatory. These observations have revealed a complex structure. The fountain is not uniform. There are regions where the outflow is strong, where supernova explosions have created large bubbles of hot gas that extend thousands of light-years above the disk. And there are regions where the outflow is weak, where the gas cools quickly and falls back down close to the disk. One of the most prominent features of the galactic fountain is the Fermi bubbles, two enormous lobes of gas and energy extending above and below the galactic centre. The Fermi bubbles were discovered in 2010 by the Fermi Gamma Ray Space Telescope, and they are some of the largest structures associated with the Milky Way. The Fermi bubbles span 50,000 light-years from top to bottom, covering a significant fraction of the sky. They emit gamma rays, the highest energy form of light, and they are filled with high-energy particles moving at nearly the speed of light. The origin of the Fermi bubbles is still debated. The most likely explanation is that they were created by a massive outburst from the supermassive black hole at the centre of the Milky Way, millions of years ago. During this outburst, the black hole consumed a large amount of matter, releasing a burst of energy that blew a huge bubble of gas out of the galactic centre. But there are other possibilities. Some scientists believe the Fermi bubbles were created by a burst of star formation in the galactic centre, a period when thousands of massive stars formed and then exploded as supernovae in a relatively short time. The combined energy from all these supernovae could have created the bubbles, whatever their origin. The Fermi bubbles are evidence that the Milky Way has not always been as quiet as it is today. In the past, there were periods of intense activity, periods when enormous amounts of energy were released from the galactic centre, reshaping the structure of the galaxy. The galactic fountain is also connected to the flow of gas into the galaxy. The Milky Way is surrounded by a vast reservoir of hot gas called the circumgalactic medium. This gas extends for hundreds of thousands of light years beyond the visible edges of the galaxy. It is very hot, millions of degrees, and very diffuse, with only a few particles per cubic meter. The circumgalactic medium is a reservoir of material for future star formation. Over billions of years, some of this gas will cool and fall onto the galactic disk, where it will be incorporated into new stars. But the circumgalactic medium is also fed by the galactic fountain. Gas blown out of the disk enriches the circumgalactic medium with heavy elements, changing its composition and affecting the future evolution of the galaxy. The interplay between the disk, the fountain, and the circumgalactic medium is a key part of the life cycle of the galaxy. Gas flows in, gas flows out, and the balance between inflow and outflow determines the rate of star formation and the evolution of the galaxy over billions of years. The galactic fountain is a hidden circulatory system, a flow of gas that connects the disk to the halo and beyond. It is invisible to the naked eye, but it is essential to the health and vitality of the galaxy. In the halo of the Milky Way, far from the bright centre and the bustling disk, there are stars that have been shining for more than 13 billion years. These are the oldest stars in the galaxy, born in the first billion years after the Big Bang, when the universe was young and the first galaxies were just beginning to form. These ancient stars are different from the stars in the disk. They are metal poor, meaning they contain very little in the way of elements heavier than hydrogen and helium. This is because they formed before the universe had been enriched with heavy elements by the deaths of earlier generations of stars. They are relics of a simpler time, when the universe was composed almost entirely of the lightest elements created in the Big Bang. Finding these ancient stars is like archaeological detective work. They are faint, dim, and scattered throughout the halo, mixed in with younger stars. But astronomers have developed techniques to identify them. By analysing the light from a star, astronomers can determine its chemical composition. Stars with very low abundances of heavy elements are likely to be very old, formed in the early universe. One of the oldest stars ever discovered is called HD 283, also known as the Methuselah star. This star is located in the halo of the Milky Way, about 200 light-years from Earth. Based on its chemical composition and other properties, astronomers estimate that it is more than 14 billion years old, almost as old as the universe itself. This creates a puzzle. The universe is approximately 13.8 billion years old, based on measurements of the cosmic microwave background radiation. How can a star be older than the universe? The answer lies in the uncertainties in the measurements. The age of HD 140283 has a large uncertainty, and when this uncertainty is taken into account, the star's age is consistent with the age of the universe. But it is close, very close, suggesting that this star formed in the first few 100 million years after the Big Bang. The oldest stars are not just interesting because of their age, they are also important because they tell us about the conditions in the early universe. By studying the chemical composition of these stars, astronomers can learn about the first generation of stars, the stars that formed before any heavy elements existed. The very first stars in the universe, called Population 3 stars, were made entirely of hydrogen and helium. They had no heavy elements at all, because no previous generation of stars had existed to create them. These stars were likely very massive, hundreds of times more massive than the Sun, and they lived fast and died violently, exploding as supernovae after only a few million years. These first supernovae enriched the universe with the first heavy elements: carbon, oxygen, iron, and all the other elements necessary for life were created in these explosions and scattered into space. The next generation of stars, called population 2 stars, formed from gas that had been enriched with these heavy elements. The oldest stars we observe today are population 2 stars, the second generation, formed from gas that had been enriched by the deaths of population 3 stars. No population 3 star has ever been observed. They all died billions of years ago, and their remnants have long since faded. But we can study them indirectly by looking at the chemical signatures they left in the population 2 stars that formed from their ashes. The oldest stars in the Milky Way also tell us about the formation of the galaxy itself. The halo stars orbit the galaxy on long elliptical orbits, plunging through the disk and then soaring back out into the halo. This chaotic motion is evidence that the halo formed from the merger of many smaller galaxies. Each small galaxy that merged with the Milky Way contributed its stars to the halo, and the random orbits of these stars reflect the violent history of the galaxy's formation. By studying the orbits and chemical compositions of halo stars, astronomers can reconstruct the merger history of the Milky Way. They can identify groups of stars that came from the same small galaxy, torn apart billions of years ago. They can trace the streams of stars that wrap around the galaxy, the remnants of galaxies consumed long ago. One of the most significant discoveries in recent years is the identification of a major merger that happened about 10 billion years ago. This merger, called the Gaia-Enceladus merger, involved a dwarf galaxy with a mass of about 600 million solar masses. When this galaxy collided with the Milky Way, its stars were scattered throughout the halo, and its gas was incorporated into the disk, fueling a burst of star formation. The Gaia-Enceladus merger was one of the most significant events in the history of the Milky Way. It added a substantial amount of mass to the galaxy and fundamentally altered its structure. Many of the stars in the inner halo today came from the Gaia-Enceladus dwarf galaxy. The oldest stars are time capsules, preserving information about the early universe and the early history of the Milky Way. Each one is a fossil, a relic of a time when the universe was young and galaxies were just beginning to form. By studying these stars, we can peer back in time, learning about the conditions in the universe billions of years ago. But finding and studying these ancient stars is challenging. They are faint, requiring large telescopes and long exposure times to observe. They are rare, scattered throughout the halo, requiring surveys of millions of stars to find even a handful of the oldest ones. And they are difficult to analyze, requiring precise measurements of their chemical compositions to determine their ages. Despite these challenges, astronomers continue to search for the oldest stars in the Milky Way. Each new discovery adds to our understanding of the early universe and the formation of galaxies, and each ancient star is a reminder that the Milky Way has a long and complex history, stretching back to the very beginning of time. The oldest stars are the elders of the galaxy, witnesses to billions of years of cosmic history. They have seen the Milky Way grow from a small collection of gas and dark matter into the majestic spiral galaxy we see today. They have watched as countless generations of stars were born and died, enriching the galaxy with heavy elements and making possible the formation of planets and life. And they continue to shine, faint but steady, a testament to the enduring nature of the universe. Above and below the disk of the Milky Way, at distances of several thousand light years, there is a phenomenon known as the galactic fountain. This fountain is not made of water. It is made of gas, hot gas that has been blown out of the disk by supernova explosions and stellar winds. Massive stars live fast and die violently. When they explode as supernova, they release enormous amounts of energy. This energy heats the surrounding gas to millions of degrees, creating expanding bubbles of hot ionized gas. These bubbles rise out of the galactic disk, driven by their own buoyancy, like bubbles rising in water. As the hot gas rises, it cools and slows down. Eventually it reaches a maximum height, several thousand light-years above the disk. Then, pulled by the gravity of the galaxy, it falls back down, raining back onto the disk like a fountain. This cycle of gas being blown out of the disk and falling back down is called the galactic fountain. The galactic fountain plays an important role in the life cycle of the galaxy. It transports gas from the disk to the halo and back again. It mixes gas from different regions of the galaxy, spreading heavy elements created by supernovae throughout the disk, and it regulates star formation, removing gas from star-forming regions and slowing the rate at which new stars are born. The fountain also enriches the halo with heavy elements. As the hot gas rises out of the disk, it carries with it the metals created by dying stars. Some of this gas escapes the galaxy entirely, blown out into intergalactic space by the force of the supernova explosions, but much of it falls back down, enriching the disk with heavy elements and making it possible for future generations of stars to form planets and, potentially, life. Observations of the galactic fountain are difficult. The hot gas emits X-rays and ultraviolet light, which are absorbed by Earth's atmosphere. To observe the fountain, astronomers must use space-based telescopes, such as the Hubble Space Telescope and the Chandra X-ray Observatory. These observations have revealed a complex structure. The fountain is not uniform. There are regions where the outflow is strong, where supernova explosions have created large bubbles of hot gas that extend thousands of light-years above the disk. And there are regions where the outflow is weak, where the gas cools quickly and falls back down close to the disk. One of the most prominent features associated with the galactic fountain is a network of high-velocity clouds. These are clouds of neutral hydrogen gas moving at speeds that are much higher than typical for gas in the halo. Some of these clouds are moving toward the disk, falling back down under the pull of gravity. Others are moving away from the disk, blown out by supernova explosions. The high-velocity clouds are important because they represent a significant reservoir of gas that can fuel future star formation. As these clouds fall back onto the disk, they add fresh material that can be incorporated into new stars. Some estimates suggest that the high-velocity clouds deliver enough gas to the disk to sustain star formation at the current rate for billions of years. But the origin of the high-velocity clouds is still debated. Some may be part of the galactic fountain, gas that was blown out of the disk and is now falling back. Others may be primordial gas, left over from the formation of the galaxy, and only now falling onto the disk. Still others may be the remnants of small satellite galaxies that were torn apart by the Milky Way's gravity. The galactic fountain is closely connected to the concept of feedback in galaxy evolution. Feedback refers to the processes by which energy from stars and supernovae affects the surrounding gas, regulating star formation. Without feedback, star formation would proceed too rapidly, consuming all the available gas in a relatively short time. But feedback heats the gas, blows it out of star-forming regions, and slows down star formation, allowing galaxies to form stars over billions of years. The galactic fountain is one manifestation of feedback. It removes gas from the disk, preventing it from immediately forming new stars. This gives the galaxy time to evolve, to enrich itself with heavy elements, and to develop the complex structure we observe today. The fountain also connects the disk to the circumgalactic medium, the vast halo of hot gas that surrounds the Milky Way. The circumgalactic medium extends for hundreds of thousands of light-years beyond the visible edges of the galaxy. It is very hot, millions of degrees, and very diffuse, with only a few particles per cubic meter. The circumgalactic medium is a reservoir of material for future star formation. Over billions of years, some of this gas will cool and fall onto the galactic disk, where it will be incorporated into new stars. But the circumgalactic medium is also fed by the galactic fountain. Gas blown out of the disk enriches the circumgalactic medium with heavy elements, changing its composition and affecting the future evolution of the galaxy. The interplay between the disk, the fountain, and the circumgalactic medium is a key part of the life cycle of the galaxy. Gas flows in, gas flows out, and the balance between inflow and outflow determines the rate of star formation and the evolution of the galaxy over billions of years. Recent observations have also revealed that the galactic fountain is not symmetric. The outflow is stronger on one side of the galaxy than the other. This asymmetry may be related to the warp in the disk, or it may be caused by recent supernova activity in specific regions of the galaxy. Understanding the galactic fountain requires a combination of observations and computer simulations. Observations tell us what the fountain looks like, where the gas is, and how fast it is moving. Simulations help us understand the physical processes that drive the fountain, how energy from supernovae is converted into kinetic energy of the gas, and how the gas interacts with the magnetic field and the dark matter halo. The galactic fountain is a hidden circulatory system, a flow of gas that connects the disk to the halo and beyond. It is invisible to the naked eye, but it is essential to the health and vitality of the galaxy. It regulates star formation, enriches the interstellar medium with heavy elements, and connects the visible galaxy to the vast reservoir of gas in the circumgalactic medium. Without the galactic fountain, the Milky Way would be a very different place. Star formation would proceed too rapidly, consuming all the gas in a few billion years. The galaxy would be smaller, less massive, and less enriched with heavy elements. Planets like Earth, with their abundance of carbon, oxygen, and iron, might never have formed. The galactic fountain is a reminder that galaxies are not isolated systems. They exchange matter and energy with their surroundings, and this exchange shapes their evolution over cosmic time. Streaming through the Milky Way, invisible and intangible, are particles moving at nearly the speed of light. These particles are called cosmic rays, and they carry enormous amounts of energy. They were discovered more than a century ago, but their origin and nature remain among the greatest mysteries in astrophysics. Cosmic rays are not rays at all. They are particles, mostly protons, the nuclei of hydrogen atoms. About 90% of cosmic rays are protons, 9% are helium nuclei, and the remaining 1% are the nuclei of heavier elements, along with electrons and positrons. These particles travel through space at relativistic speeds, close to the speed of light. When they strike Earth's atmosphere, they collide with air molecules, creating showers of secondary particles that rain down on the surface. These cosmic ray showers were first detected in the early 20th century, and they led to the discovery of several exotic particles, including the muon and the pion. Cosmic rays carry enormous amounts of energy. The most energetic cosmic rays ever detected have energies exceeding 10 to the 20 electron volts, more than 1 million times the energy of particles produced in the Large Hadron Collider, the most powerful particle accelerator on Earth. A single cosmic ray particle with this energy carries as much kinetic energy as a well-thrown baseball, concentrated in a single subatomic particle. Where do cosmic rays come from? This is one of the great unsolved mysteries. For lower energy cosmic rays, the answer is reasonably well understood. They are produced by supernova explosions. When a massive star explodes, the shockwave from the explosion accelerates particles to very high energies, turning them into cosmic rays. The mechanism is called shock acceleration, or Fermi acceleration, after the physicist Enrico Fermi who first proposed it. As the supernova shockwave expands through space, particles bounce back and forth across the shock front, gaining energy with each crossing. After many crossings, the particles reach extremely high energies and escape into interstellar space as cosmic rays. Observations support this theory. Astronomers have detected gamma rays coming from supernova remnants, the expanding shells of gas left behind by supernova explosions. These gamma rays are produced when cosmic rays collide with gas in the remnant, and their detection confirms that supernova remnants are indeed sources of cosmic rays. But supernova remnants can only accelerate particles to a certain energy, about 10 to the 15 electron volts. Beyond this energy, The particles escape from the remnant before they can be accelerated further. So where do the highest energy cosmic rays come from? This is the great mystery. The highest energy cosmic rays, those with energies above 10 to the 18 electron volts, cannot be produced by supernova remnants. They require more powerful sources that can confine particles long enough to accelerate them to such extreme energies. Several candidates have been proposed. One possibility is supermassive black holes in the centers of galaxies. As matter falls into a supermassive black hole, it forms an accretion disk, and powerful jets of material are launched from the poles of the disk. These jets can extend for thousands of light years, and they are filled with high-energy particles and strong magnetic fields. The jets could accelerate particles to the highest energies observed in cosmic rays. Another possibility is gamma-ray bursts, the most powerful explosions in the universe. Gamma-ray bursts are thought to be produced by the collapse of massive stars or the merger of neutron stars. They release as much energy in a few seconds as the Sun will release in its entire lifetime, and they could potentially accelerate particles to ultra-high energies. A third possibility is exotic sources, such as the decay of dark matter particles or the evaporation of primordial black holes. These sources are speculative, but they cannot be ruled out. One clue to the origin of cosmic rays comes from their composition. By measuring the relative abundances of different elements in cosmic rays, astronomers can learn about the sources. For example, cosmic rays contain a higher proportion of heavy elements than is typical for the interstellar medium. This suggests that at least some cosmic rays come from regions where heavy elements are abundant, such as supernova remnants or the winds from massive stars. Another clue comes from the arrival directions of cosmic rays. If cosmic rays came from specific sources, such as supernova remnants or active galactic nuclei, we might expect to see more cosmic rays arriving from the directions of these sources. But observations show that cosmic rays arrive from all directions almost uniformly. This suggests that cosmic rays are scattered as they travel through the galaxy, their paths randomized by magnetic fields. The magnetic field of the Milky Way plays a crucial role in the propagation of cosmic rays. Cosmic rays are charged particles, and charged particles are affected by magnetic fields. As cosmic rays travel through the galaxy, they spiral along magnetic field lines, bouncing back and forth. This magnetic confinement traps cosmic rays in the galaxy, preventing them from escaping into intergalactic space. The typical lifetime of a cosmic ray in the Milky Way is about 10 million years. During this time, a cosmic ray travels a total distance of about 1 million light-years, bouncing back and forth through the galaxy many times before finally escaping. This long residence time means that cosmic rays are well mixed throughout the galaxy, which explains why they arrive at Earth from all directions. Cosmic rays also play an important role in the physics of the interstellar medium. They carry energy, and when they collide with gas, they transfer some of this energy to the gas, heating it. This cosmic ray heating is an important source of energy for the interstellar medium, particularly in dense molecular clouds where starlight cannot penetrate. Cosmic rays also affect the chemistry of the interstellar medium. When cosmic rays collide with gas molecules, they ionize them, stripping away electrons. This ionization affects the chemistry of the gas, influencing the formation of molecules and the rate at which gas can collapse to form stars. In dense molecular clouds, cosmic rays are the primary source of ionization. Without cosmic rays, these clouds would be almost completely neutral, and the chemistry would be very different. Cosmic rays create ions, and ions interact with neutral molecules, driving chemical reactions that produce more complex molecules, including some of the organic molecules that are the building blocks of life. Studying cosmic rays is challenging. They are difficult to detect directly because they are rare. At sea level, about 1 cosmic ray particle passes through each square centimetre every second. This may sound like a lot, but it is very small compared to the number of other particles around us. Detecting the highest energy cosmic rays requires enormous detectors, covering hundreds or thousands of square kilometres. One of the largest cosmic ray detectors is the Pierre Auger Observatory in Argentina. It consists of 1,600 detectors spread over 3,000 square kilometers. When a high-energy cosmic ray enters Earth's atmosphere, it creates a shower of billions of secondary particles. These particles spread out over a large area, and by detecting them with multiple detectors, astronomers can reconstruct the energy and arrival direction of the original cosmic ray. Another way to study cosmic rays is by observing the gamma rays they produce. When cosmic rays collide with gas in the interstellar medium, they produce gamma rays. By mapping the distribution of gamma rays in the galaxy, astronomers can learn about the distribution and properties of cosmic rays. The Fermi Gamma Ray Space Telescope has made detailed maps of the gamma ray emission from the Milky Way. These maps show that gamma rays are brightest along the galactic plane, where the density of gas is highest. They also show bright spots associated with supernova remnants and other potential sources of cosmic rays. Cosmic rays are a hidden component of the galaxy, invisible but pervasive. They carry energy, they heat the interstellar medium, they drive chemical reactions, and they influence star formation. And yet, despite more than a century of study, we still do not fully understand where they come from or how they are accelerated to such extreme energies. The mystery of cosmic rays is a reminder that the universe still holds many secrets, and that even the most familiar objects like our own galaxy can surprise us with phenomena that challenge our understanding. As we conclude our journey through the biggest secrets of the Milky Way, we are left with a sense of wonder and humility. The Milky Way is not just a collection of stars, it is a living, dynamic system, shaped by invisible forces and hidden structures that we're only beginning to understand. We've explored the invisible architecture of the galaxy, the dark matter that holds it together, and the supermassive black hole at its center. We have journeyed through the spiral arms, where new stars are born, and we have witnessed the deaths of stars, the explosive supernova that enrich the galaxy with heavy elements. We have discovered the magnetic fields that thread through the galaxy, the satellite galaxies that orbit it, and the future collision that will reshape it entirely. Each secret we uncovered revealed new layers of complexity, new mysteries waiting to be solved. The Milky Way is our home, a vast and ancient galaxy that has existed for more than 13 billion years. It will continue to exist for billions of years to come, growing, evolving, merging with other galaxies, and creating new generations of stars. And we, tiny and fragile as we are part of this grand cosmic story. We are made of stardust, the atoms forged in the hearts of stars that died long before the sun was born. We are children of the Milky Way, born from its gas clouds, nurtured by its light, and destined to explore its secrets. Thank you for joining us on this journey through the biggest secrets of the Milky Way. May you rest well under the stars, and may your dreams carry you through the infinite wonders of the cosmos. Clear skies.